Hey, we're live here at the HVAC School live stream. We've got a couple awesome guests. You guys want to introduce yourself? Let's start with Mr. Kaiser there.
Hey, Matt. Thanks. I'm Eric Kaiser from True Tech Tools, and I've been on a couple live streams around here before, so people, may or may not know me. But gonna hang out tonight and have some fun, huh?
Yeah.
Nice.
And then Mr. Fultz, tell us a little bit about yourself.
Yes, sir. Thank you, Matt, for having me. Hello, everyone, tonight. Glad to be a part of the HVAC School evening event here. And I am with White Rogers by Copeland. Copeland is our overall name of the company. White Rogers is the division I'm in, and been living and breathing heating and air conditioning since 1989. So I think this puts me at about 35 years this year, and love the industry. Great industry to be a part of, and privileged to be able to share a little bit here with everyone tonight.
Yeah, thanks for coming on, both of you guys. So this topic comes up every winter, and Adam wrote a great tech tip recently on that. So Adam, do you want to kind of just take us through a little bit about your thinking on writing this recent tech tip, and tell us a little bit about what is heat pump COP?
So COP is coefficient of performance, and the whole point of writing the tech tip was, I think, kind of across the entire country, we were seeing a pretty big cold snap, right? And I just saw on different, Facebook pages and forums and that contractors, builders, all kinds of advice going around for people with heat pumps to switch your heat pump over to emergency heat. And I think there's a big misconception of when you should use emergency heat and how you should set up a heat pump. And that was kind of my thought process behind writing the tech tip, which is good cop, bad cop.
I like that. So Eric or Jim, either one of you guys could take this one, but how are we supposed to think through that process of when that resistance heat is supposed to come on for a heat pump?
Well, I mean, realistically, with resistance heat, when we're using resistance heat, we don't want it to come on ever, if possible. We want it to come on as little as possible, because in almost all conditions, the heat pump is going to be more efficient. It's got to get really, really cold outside, like serious negative Fahrenheit numbers, before we start seeing a heat pump compressor actually approach a 1 COP. And anytime we see higher than a 1 on the COP scale, that means that for the same amount of energy as electric heat delivers BTUs, the heat pump is delivering like 1.5 or 1.8 times that, or 2 times that, or 4 or 5 times that much heat for the same wattage input. So it's using less energy for the same amount of heat being transferred into the house, because we can transfer it out from outside to inside with refrigeration more efficiently.
So one way I like to describe this to people is resistance heat is like, think of it, if you're paying for 1 unit of heat, you pay $1 for 1 unit of heat, you get 1 unit of heat in your house, right? It's 100% efficient. And for like, let's say you have a COP of 2 or a COP of 1.5 or whatever, you pay $1, but you're getting $1.50 worth of heat in your home, or $2 worth of heat. It's like a bargain deal, if you will, for heat.
It's a good way to think of it. I like that.
Yeah, so it pays for itself, is what you're telling me.
It's free.
It's free. It's free energy.
There you go.
It's more efficient use of energy. How about that?
Yeah. Okay. So where did this misconception? So why are people setting their heat strips to come on? What do you guys think that the main factor is there?
Jim, you've been doing this longer than the rest of us. You want to take that one?
Well, I would just simply go to homeowner comfort. That's probably the number one reason I would know of why that backup heat is kicking on. Is you get down to that COP below 2, you're 1.5 or pushing 1, and it's cool air coming out of the registers, and when you're not creating that much additional heat from that heat pump, the homeowner is wanting something that they actually feel some warmth coming out of the register. So my experience has been just simply a comfort level rather than recognizing that there's still some efficiency there.
Yeah, I mean that is a big thing, but that brings us to like the number one rule of heat pumps, which is don't blow air on people.
Yep.
Right? Thank you, Ed. Right? Like that's
There he
the whole
is.
point of Angry Ed.
There you go.
You know,
Yeah.
Ed says don't blow air on my head.
Yep.
You know, that's what makes him angry.
Gotcha.
So go ahead, go for it, Matt.
Do you want to take us through some of these slides here?
Sure. So this is this slide is some performance of two different what I call airflow controlled inverter units. So it's an inverter compressor, but the speed of the compressor is defined by the amount of air going across the indoor coil. So if you put enough air across the indoor coil, whether it's in cooling, it removes heat. If it's in heating, it adds heat into the airstream. But the more air you put across that coil, the faster that compressor is going to ramp up to a certain speed. So this is an airflow controlled inverter unit. I picked out a 3-ton and a 5-ton matchup. I threw it into these charts, and this is just some stuff that I use to graph these things out to visualize things. It's pretty easy to do in a spreadsheet program. And I want to sit here and point at the screen, so I'm going to point at things, and you all are not going to know what I'm pointing at.
Mm-hmm.
I need my laser pointer.
Use your words, Eric.
Use my words. Oh, geez.
I'll also say you're really good at PowerPoint, or not PowerPoint, Excel. If you can do this in Excel, I feel like that's pretty amazing.
This is not Excel. This is actually Apple's program called Numbers.
Oh,
and it is really stinking easy to do that. Like it is honestly, you can put together one of those charts once you get the all the data put in, and because there's some formulas in this to make all the calculations. Once you get all that put in, all it is just plugging the data in and setting up the graph. You can do it in 10 to 15 minutes.
Gotcha.
Once you figure it out, just play with it. Like it's this stuff is not rocket science out here. It's not difficult. There's a lot of other things that we do in this trade that are way, way harder than this. Sit down at your computer, get yourself an hour, and start playing around with it. Excel, to me, is a much harder program to use because it has way more complications in it. I would start out using, if I recommend somebody to start out, if you've got Apple, use their Numbers program. If you've got Google, jump on their Google Sheets program. I find those a much lower lift because there's not as many features in there to try to figure out. They're not as complicated, and they don't have the really super high level user features that most people like us don't need.
Gotcha. So yeah, walk us through these. What are you wanting to show here with these?
So both of them, I'm showing the performance, right? So if you look up at the top graphs, on the left side, we've got your outdoor temperature. Next to that, we have our corresponding heat pump BTU output. At that outdoor temperature, we have the wattage that's being drawn by that heat pump to produce that amount of heat. And then to the right of that, we have our COP column, which is our coefficient of performance. So if you look at like that 3-ton up there at -4 degrees, it's got a COP still of 2.1. All right. Nice. Which means that at -4 degrees outdoor temperature, I am producing 21,100 BTUs, right, with less than half the amount of watts that it would take to produce that same amount of BTUs with electric resistance heat. So over to the right, the resistance BTUs per hour is the equivalent BTUs. So it's your wattage times 3.412, which is our BTU per watt calculation for resistance heat. That would be the equivalent BTUs per hour if I was just putting out resistance heat. So I did that to show the difference between the two, right? And then when you get down on the graph, it graphs out the resistance BTU versus the heat pump BTUs to show how much disparity there is between those 2 points on those heat pumps. And it's the same thing whether you do the 3 ton or the 5 ton, then the values are a little bit different, but it's right in that a very similar range.
Gotcha.
Now,
and same thing for these charts, like.
Well, so this one's a little bit different. Okay.
Okay.
So one of the things that some people will say is that, okay, and I flip-flop 3 to 5 ton left to right on this one. A lot of people will say, all right, what about defrost? Well, defrost reduces your COP. Yeah, it does a little bit. But this is actually a single stage 14 SEER 3 ton and 5 ton units. That's what I stuck with when I put these together. And these particular units happen to their manufacturer's performance data happens to go down to -3. All right. So if we look at that at -3 on the 5 ton, I've got a COP of 1.6. And on the 3 ton, I've got a COP of 1.4 at -3 degrees Fahrenheit. Right. Which tells me that even at -3 degrees Fahrenheit, I am still producing heat less expensively with that heat pump than I could by running straight electric heat. So I'm still getting more heat for my money. Now, it's probably not going to be enough to heat the house. In fact, I can almost guarantee you it's not enough to heat the house, but it can heat a portion of the house. And we'll get into that as we go on farther. But the other piece to this is this particular manufacturer that I got the data from actually corrects for the defrost.
Oh,
so they take that defrost time out of there, and there's some more information we'll show later on in that about how that works. You can kind of see a jump up around 47. We kind of see some things level off there in performance a little bit because that's about where we quit defrosting. Right? Mm-hmm. And then when we swing down below 27, when we get colder outside, we actually get slightly less defrost cycles because we don't have a large amount of moisture in the air because the air is then below freezing. Gotcha. As opposed to just the coil being below freezing and the air still being above freezing.
Yeah. I mean, it is amazing to think that you can still pull so much heat out of really cold air like that. What's absolute zero? What's the temperature? Isn't it like -2,000 something?
Well, it depends on which temperature scale you're on. So are you on Fahrenheit? It's like 470 something.
459.67.
Okay, 459, 460.
Yeah.
So -460.
Yeah, on the Fahrenheit scale.
And there's still, that's one of the things that I think is important to understand, that I think a lot of people, you hear everyone talk about that heat pumps aren't efficient because there's no heat, to pull in from outside. There's no more heat in the air, so you can't use them. But there's heat in the air all the way down to -460.
There's heat in the air. It's just that we're inserting ourselves, our human bodies, into that idea that there's no heat in the air because it's cold to us outside. Right? We walk outside, we feel cold, therefore there's no heat in the air. And, the nice quotation marks there. So we're inserting ourselves into that. Now, what we run into, why our heat pumps can't pick up as much heat at that point, is we're running into the limits of the vapor compression system of the refrigerants that we use and things like that, because, we start getting a wider and wider compression ratio because the coil temperatures are farther and farther apart.
Yeah. Yeah. And so from my understanding, some of the ways around that are like the vapor injection on the variable speed units and things like that.
Yeah, there's a lot of different ways to manage that.
I'm
not necessarily an expert on all of that refrigerant system engineering, so I'm not going to pretend.
Yeah. Okay. Now, is there anything else you want to hit on this one here?
Now, this one here, This was what I wanted. So go ahead, Jim.
Yeah, go ahead, Jim.
Can we catch 2 slides back? And I want to add another different path here that we've been talking about here so far, and maybe run this parallel with Eric with where he's going. And first of all, just simply to help those who are listening, we're looking at a balance point, and balance point is something that really has 2 different definitions. And what we're talking about tonight is the balance point of the efficiency and the capacity, and probably more along on this slide, the actual capacity of the heat pump. But Eric's taken this to another level by showing us what the resistance BTU heat is, which would compare the actual efficiency of the unit. And that COP is dealing with our efficiency of how efficient the heat pump is versus the backup heat. And so capacity would be another level of, if you have enough capacity when you're getting down to 17 or well below the capacity of that heat pump. And when you, thank you for the slide here.
Yeah, there you go.
The thermal balance point for capacity, the colder it gets, the less heat, the less BTUs that heat pump's making. And at some point, you're going to have to add another type of heat to be able to take care of the load. So that's the capacity that we're going to. All right, let's head back to that other one, because that other one's really where I want to focus on. And with that, I would probably put another column on this chart. We have the resistance BTUH, and we could put another column on there that would deal with the amount of gas or fuel that a gas furnace would take at those same levels. And so just to try to make this a little easier to understand here, and we know that the balance point for efficiency between resistance heat and the heat pump is that COP of 1. Eric did a wonderful job of defining that, but it's different for a gas furnace. Well, how do you compare when a gas furnace is more efficient than the heat pump? And that's a little bit bigger of a formula to get to that.
Because that's not necessarily efficiency and energy use. That's actually cost efficiency, right? Is where you're going with that, I think.
So, like, just to clarify this, what we've been talking about, what you've been talking about so far has been thermal balance point. That's where we've been kind of starting off, and now you're transitioning over into
economic balance point.
Economic
I think is what that's called, right?
Balance point. And that's the thing there. We call them both balance points, but there is a difference between the two. And so maybe I can give a little definition of the economic balance point. We can head back to the thermal. Then the economic balance point on this would just simply be the way that I did it as a contractor in the past. I would actually go to the manufacturer specs and find out how much heat that heat pump was making. And in their specs, you're getting 47 degrees and 17 degrees for how much BTU output you're going to get out of that heat pump. And then with that, you go to your local utility company, find out how much it costs per kilowatt hour, and you can actually calculate how much money it's going to cost to use that heat pump. Now, to compare with a gas furnace, you'd size your gas furnace, and say you had a 100,000 BTU gas furnace, and it was an 80% efficient furnace. So your number would have to subtract that 20% off for the actual BTUs you was getting out of that, and you would take that furnace and say, okay, I'm getting 80,000 BTUs out of that. How much does that cost? How many gallons? And most of the time it's propane that we're dealing with out in the country here in California. How many gallons or part of a gallon of propane do I need to get 80,000 BTUs? And once I got that number, then I can multiply that by the cost, my local cost of propane. And that gives me how many dollars it's going to cost for 80,000 BTUs of heat. Then I can go over and I can take my heat pump number, and I can, whatever BTU that is, I can find my multiplier to get it up to 80,000 BTUs. So I'm getting the same amount of heat, and I take how much electricity that's going to cost by the kilowatt hour and multiply that up to 80,000 BTUs. And I can compare how many dollars or cents the heat pump's going to give for 80,000 BTUs at 47 degrees or 17 degrees, or in a chart that Eric's showing here, at any degree we would want to. You basically make another column and put on there how many gallons of propane it would take on an 80% efficient furnace to equal that same rate. Hopefully I didn't get too much in the weeds there, but there is a way to calculate your cost, your efficiency cost of that heat pump versus of the backup heat. When are you going to do that? More likely on a dual fuel rather than electric resistance, because we do have that COP, that number for the resistance heat, of knowing when the resistance heat is equal in efficiency, but and that's going to be equal in cost as well, not only in efficiency but of cost when we have a COP of 1, and being able to take that and transfer that into numbers where we can actually see how much that gas furnace is costing us, how much that heat pump is costing us, and be able to make our cutoff when we're going to be paying less for the backup heat than we are for the heat pump.
Right.
Gotcha.
So I think like it does get, when you're actually comparing like economic, it does get super complex. And if you're really trying to be detailed, like you said, it's 47, 17. There's a couple different, if you really want to be thorough, if you actually look at ACCA's Manual H, they talk about actually going through each one of ASHRAE's bin temperatures, the bin data, and calculating the difference in cost at each one of the bins in your individual area. So things about heat pumps, obviously, to understand is you could have the same model heat pump in two different areas of the country, and your heat pump might live at one COP a good majority of the time versus another place in the country where it might be quite a bit less efficient. So just because they're the same unit, it's not the same efficiency based on the outdoor temperatures.
Mm-hmm.
Yeah, and for that, you really got to look, like you said, at bin data. How many hours a year are you going to run at these temperatures? For me, where I'm at, and even you, Adam, probably where you're at, you're going to see a lot of the year above that 17 degrees there.
Mm-hmm.
There's a significant amount of the heating season. We might get several weeks where it's below 17, but there's months and months where it's above 17 degrees most of the time, or hours really, because the temperature changes throughout the day. And we're going to see in a couple more slides here, we'll get into a little bit more of that balance point, the thermal balance point between the house and the heat pump.
Is it?
Yeah. So just real quick on this one, what I wanted to show, I pulled, this is a 14 SEER single stage, and the particular manufacturer that I got the data from pulled it out. They showed the rated BTUs, and then they showed BTUs minus the defrost cycle. Right. And I wanted to show the difference in COP there. Right. So if you look across the left, it shows you the wattage, it shows the rated BTUs, the rated COP, then the BTUs minus the defrost and the minus defrost COP next to that. Then I'm showing the net BTUs per hour reduction. And you notice that at 47, we stopped getting a reduction for defrost, right? Because we're not really going to see any defrost cycles above that 47 number. But if you look over to the right, like where's the primary reduction by that defrost, it's around that 27 degree mark. And as we go down, we actually lose a little bit of percentage there because we're not seeing as many defrost cycles.
No, I'm questioning like how accurate this is if you actually have a system with demand defrost, right?
Yeah, that's going to vary a lot. Now,
so this is timed.
This particular one is time defrost, yes. And to Adam's point, you're going to see typically less defrost cycles with a demand defrost. because it only does it when the coil needs it rather than when the timer says to do it.
But reality is the difference between the rated and then the minus defrost COP is only what, 0.2, 0.3. So we're not talking a huge amount of difference between the two. And to the point, there are some areas of the country that's going to have more moisture in the air, and for the audience, the reason that number is higher, if you've ever heard psychometrics without tears, you would know that there's more moisture the warmer the air is. So as the air continues to get cooler, there's less moisture and less, you're dealing with less amount of BTUs there because less amount of defrost to get rid of.
Yeah, thank you, Gene. Appreciate that. But and the to me that also right there, this chart here negates a lot of the arguments that I hear about, oh, well, that doesn't include defrost, because yes, you can include defrost times in there. You can include that in there. And the COPs are still above 1, even at -3 degrees Fahrenheit with a base. I mean, this is like your most basic heat pump you can get on the market right now. So everything else above this is going to have better COPs.
Right. This is not your Mitsubishi Hyperheat. This is not
No.
the Carrier Green Speed. This is
this is a freaking single stage 14 SEER bare bones builder grade heat pump.
Yeah.
You know, and we're still seeing a with the defrost cycles factored in, we're still seeing a COP of 1.4 with that at -3 Fahrenheit. So to me, that negates the entire argument. And I'm going to show here on the next slide what people are talking about, where they go from where they try to say to turn things off. Now, I took that 3-ton airflow controlled inverter heat pump. You'll see the pink, the green line is the heat pump performance curve. All right. Mm-hmm. The blue line is my load slope on the house. So as it gets colder, load keeps increasing. And we're going to say on this one that the calculated load is somewhere around that -3 point. Okay. This actually worked out really beautifully when I calculated all this out, because this is actually an actual load slope that I used. And this piece of equipment would work really well for this house. You can see where the green line and the blue line intersect is somewhere around 17 degrees. So that means at 17 degrees, I'm going to run out of heat with that heat pump. I can't heat the house 100% to demand with only the heat pump. But the red line down there, remember, that's my resistance BTU equivalent. That's the equivalent BTUs that would get out of a resistance heater that I'm running the wattage into that heat pump. So that's the wattage going into the heat pump equivalent to the resistance. So I'm still getting way better performance. My COP at 17 was still above, well above 2 with this unit.
So the COP of 1 would be if the green line and the white line, or the green line and the red line met.
Yes. When they meet, that's your COP of 1.
Okay.
So why would I shut that heat pump off? Because I'm still getting less expensive heat. I can't heat the house 100%. And I shouldn't be. Okay, yes, this is air to air. Great question.
We should have got into that.
Really doesn't matter on this because it's the same thermal. We're transferring heat from point A to point B. We can do air to air. We can do air to water. We can do water to air. We can do water to water. We're still transferring heat from one fluid to another fluid.
If we were doing water to air, the bottom line would be whatever your well temperature is or water income temperature. It wouldn't go from 67 down to -4. It would be a constant 58 or 55 or whatever temperature your water is. So that number would never change.
Well, it would if we're looking at the house slope.
The load would change.
The load slope, you would still have that there. But your other side of the refrigerant system, you're right. And I'm gonna disagree with you slightly there, Jim. It will change slowly over the year, but it's not going to change drastically immediately in the same way that air does. because I've run into water source systems where I'm running my loops below freezing. They got to have glycol in them. There's a reason they put glycol in those, because after they extract so much heat out of the ground over the year, they run out of heat.
I was talking about open loop.
Open loop's probably a different, open loop or a pond loop, something like that. Yeah. That's a different story.
Yeah. Or as we call them, pump and dumps.
Yeah. Pump and dump systems. That there again, that's a different story, and it depends on your water source.
Correct.
But they stay a lot more stable. Yeah. The closed loop systems, I've run up onto some big problem systems. If people don't do closed loop right, it gets really ugly.
Mm-hmm.
Right. Yeah. So when you have a consistent temperature, like an open loop or a ground source or whatever, basically what you're saying is, if you're looking at any of these charts, the COP fluctuates drastically based on outdoor air temperature. But if you have one of these type of systems that we're just talking about, the COP stays in a much tighter range.
Absolutely.
Yeah.
Yes.
Because you're in that case, evaporator coil or your outdoor coil, your heat source coil, is not really ever changing temperature drastically.
Yeah, you wouldn't see this green line wouldn't fall off very much.
Right, because
pretty much be a flat line.
That water temperature might be consistently up at 57 degrees, so you're always going to have that 35,000, 36,000 worth of heat there, unless that water temperature starts falling.
And that can happen. And a couple reasons to give a little more definition to that, Eric. Over time, over the winter, that happens. And it happens due to several different factors. One could be depending on your environment. If your ground's frozen, you don't have a lot more moisture content going down into where that loop is, and the soil around that loop is drying out. The drier it gets, the less heat transfer can go through that soil, and that compromises how efficient it is. But it's not near the drop as what we're seeing here with an air to air.
No, unless you have a closed loop system that loop is not sized properly, you should never see loop temperatures. You should really never see loop temperatures below 30. I mean, if you're seeing loop temperatures, returning water coming back into that unit below 30, you got a serious loop problem. You've oversized your unit for your loop. You're trying to draw too much heat out of that ground. I mean, and it does happen. One of the first, I'll never forget, one of the first geo or ground source systems I walked up on was a summertime. It's a brand new unit. And the homeowner had hired their own well contractor for a closed loop system. And they were complaining about that it wasn't keeping up in the house. And I found that loop water temperature over 110 degrees.
Wow.
Return coming back to I was like, I called my boss because I'm green. I don't know hardly anything about this. And he's like, oh, that's not good. We're not going to be able to put any more heat into that yard.
Well, do you want to finish up on this slide here, Eric?
So back to this slide, right there around that 17 degree mark, probably 18 degrees. If you ran a line up there, you'll notice there's a pink line up top. All right. And that's 5 kW of resistance heat. So what happens is, with a well set up control system, now this is all dependent on how the controls are set up. All right. When we hit that thermal balance point where the heat pump won't keep up with the demands of the house, then we bring on auxiliary heat. We're bumping that heat up just a little bit. We're adding some extra heat to that heat pump, because I still want my less expensive heat that heat pump can produce, even though it can't all keep the house at temperature or at set point. But I'm going to cycle that electric heat strip off and on, just like a thermostat would with a gas furnace or regular electric heat, or even the heat pump when the capacity of the heat pump is above the loads of the house. We're going to cycle it off and on to be able to meet the needs of the house. So now I'm going to keep that heat pump running 100% of the time. Once the green line is below the house line, and I'm going to cycle that auxiliary heat off and on, off and on, off and on, off and on, until it hits the thermal balance point of the heat pump plus the auxiliary heat. And if you look up in the graph up there on top, you can see the aux heat 5 kW. Now that is the heat pump plus 5 kW. So at 17 degrees, I'm getting 28,000 BTUs out of that heat pump. And at my additional 17,000 BTUs from that 5 kW heat strip, I'm getting 45,000 BTUs out of the system. So that's why I'm going to have to start cycling that electric heat off and on.
Just I wanted to make one point on this, what you're saying here. Everyone needs to keep this in mind too, when they're setting up these controls, because the heat pump, we're talking about COP, coefficient of performance, and when you're over 1, it's more efficient to run than resistance, right? So that 28,000 that you just mentioned, that's cheaper. I don't want to say it's cheap, but it's cheaper heat, right? And then the 17,000 is expensive heat. You get a portion of expensive heat and a portion of cheap heat, and you add them together and you get more heat, right?
But it's still less expensive than doing all of that work with resistance heat, which is what happens if you shut your heat pump off and go to emergency heat only, because then you're killing that less expensive heat that the heat pump can produce. Right? And I'm going to 100% expensive heat that's your emergency heat.
Yeah, you want to chime in on that, Jim?
Well, I just simply, the question that I would get on that is, and what I'm thinking about is the technician saying, okay, how do we do that? How do we get that electric resistance heat to cycle? And one of the things there's 2 ways to wire this. One, you have the call for the heat, the Y call, I would call it, going to the heat pump. And if you take that power that's powering the heat pump, go to a thermostat that you put outside to set at 17 degrees. When it gets 17 degrees, it closes and it sends power back to the resistance heat. And at that point, the resistance heat's going to continue to be on constantly until the heat pump shuts off. And so to be able to cycle that resistance heat, what you really need to be able to do is to have an additional wire going outdoors and set up as the second stage of your heat in your thermostat. So you got your main heat coming through the Y, and then you got your typically like a W2. That second stage, that wire is going out there to that outdoor thermostat and coming back to the resistance heat, so that when the system has dropped an additional degree and is not being able to maintain that house temperature, that resistance heat comes on. Once it goes back up, the resistance shuts back off, but your heat pump is running nonstop through there. So you need to run that second circuit, that second wire to the outdoor unit for that thermostat to be able to cycle that resistance heat on, rather than turning it on and losing your efficiency of what you could be getting out of the heat pump by not letting it run continuously.
Yeah, I mean, and that is exactly the way that I used to wire them when I first started in this industry. And it kind of funny, I started in the industry in 2004. My boss was doing this way back into the late 80s and early 90s with heat pumps. And he told me the story of a brand new subdivision, all electric, that went in the town. And the builder in there had his HVAC contractor that he used for most of the houses. But one of the houses was a good customer of my boss's. And he came and said, look, hey, I want you to, his name was Rich. And he said, Rich, I want you to do the HVAC in my house. And because this was an all electric subdivision, the local utility company was really watching this closely. It was one of the first ones locally that they had put in with heat pumps. So they were watching the performance of all these houses and how many kW they were using over the winter period. And after about 2 years, they came back to my boss and they said, what did you do to that house? Well, we always wired in an outdoor thermostat to trigger, to activate that heat, that auxiliary heat. And everybody else did just bang everything on, they might be banging on 10, 15 kW of heat. Well, we would bring on
temperature. It was like if it outdoor thermostat made.
Oh no, they would just bang it on with the second stage heat call.
Oh, okay.
So if there was a droop or something, then it would just.
If there was a droop, man, it was bang. And of course, this was back in the days of, if you were lucky, you had a chronotherm.
Yeah, I call that unlucky.
But yeah, I call that unlucky too. But in the day, it was the whiz bang thermostat. But most thermostats back then were even just, they were a 2-bulb mercury thermostat. So you had to have like a 2-degree droop to hit that second stage. But yeah, as soon as it hit that second stage, that's how they cycled in and out of that second stage, was with the second bulb on that mercury thermostat. And they would just bang on every bit of electric heat they had. And it was uncomfortable as all get out. Or they told their customer, when the heat pump couldn't keep up anymore, go over, switch it off, and turn on the emergency heat.
Yep.
Because they didn't put in the correct controls. And I've seen a bunch of questions in there. How do you do this? How do you wire this in? Today, we have electronic controls, and a lot of the thermostats. Jim can probably talk about, Emerson thermostats.
Matt actually has one on the screen.
White Rogers there. Well, no, just your wall thermostat, wall control.
That's what this is. This
yeah,
is,
yeah. Talk us through that, Jim. What are the best options available?
Well, yeah, I should go back here on my shelf and grab one. Our Sensi Touch 2 now has a balance point for that built into it. So you can actually set a balance point at what temperature the outdoor would be, where you want that resistance heat to be able to cycle on for you. And that's based off of, it's a Wi-Fi thermostat, so it's getting your zip code and your local outdoor temperature from that. It's could be within a degree or two, depending on where you're at and where that is reading. But that thermostat does have that ability to cycle the resistance on and off when you hit that balance point, and or you can shut off the heat pump if you want to. But at this point, with the low temp compressors and everything that we got going on, there's less and less value for even cycling that heat pump off outside.
Nice.
I would never cycle a heat pump off. If my auxiliary's resistance, or my secondary heat source's resistance, let that sucker run.
So I think a lot of different thermostats, like Sensi is one, and then the communicating systems like Carrier, like Train, Daikin, Mitsubishi, a lot of those actually look at an outdoor thermistor in the outdoor unit, which is sensing the outdoor temperature. So you don't have to run an extra wire to monitor the outdoor. And a lot of these systems, Ecobee is another one.
You would have to know your balance point.
Yeah, you really need to calculate your thermal balance point. And again, it's calculated. Now, there are some controls out there that can do it on indoor temperature droop. So when they see that compressor running 100% of the time, or they start to see indoor temperature droop, but if they're running 100% of the time and they don't see a rise in temperature after, an hour or whatever time frame that is, then they will start cycling off and on that electric heat, that auxiliary heat. And that's all in how you set these controls up. And they're not so much a thermostat anymore. We still call them a thermostat because it's for the same reason, we call this thing a phone. It's not much of a phone anymore. It's mostly a handheld computer now, but we can't run around calling it that. It's all about the setup. It's all about how you make them work.
The one that you have on the screen, it's a Daikin thermostat, right? And if you look at T on, T off, that's actually the control set point for when the auxiliary heat is going to cycle. So T on, the thermostat has to droop 3 degrees under set point for the auxiliary heat to come on, and T off means you have to surpass the set point by 1 degree Fahrenheit in order for the auxiliary cycle to end. But there's all different. You could customize for, I think almost every thermostat will give you some kind of customizable droop.
Yeah, I
Yeah.
mean, I used Jim. Cover your ears real quick. I used Honeywell for a lot of years.
All right, so I get to put another plug in. We have a universal defrost control that you can swap out, and the picture you got up here right now is your mechanical outdoor temperature sensor. Our universal defrost control has that temperature sensor built into it, so just
Cool.
simply swapping that out, and the other piece I like about that is the fact that if you are on one of the big brands that are using a time defrost type of a cycle, by replacing that defrost control, you can choose whether you want timed or demand. Now, why somebody would want timed, I'm not sure, because you can convert any heat pump over to a demand defrost and save those additional cycles where that heat pump is checking, and have that additional outdoor temperature sensor to be able to run that extra circuit if you got the wires. If you don't got the wires, then you use something like the Sensi Touch 2, where you can do it with getting that temperature directly from the internet. There's my plug.
I
Yeah, I
love
wanted
it. That sounds like a great
What's
product.
Yeah.
what's the model of that? What is it called?
the defrost board.
The defrost?
Yeah.
Yeah.
It's just
you put me on the spot.
sorry.
I'm gonna have to-
You don't have to.
You can tell he's a tech guy and then not the salesman, because the salesman would have had that part number right on the tip of his tongue,
Yeah.
just like that.
Oh yeah, I should. I'm gonna get fired for this. 4701 U-843. Say it again. 47D01 U-843.
Nice.
It's a
Cool.
nice little product there.
Yeah, that is nice.
Yeah, I like
Um,
that.
I wanted to circle back to one thing we were talking about, was the homeowner's experience of, maybe lukewarm air kind of blowing on them, and that kind of being a big factor. You go to someone's house and you say, well, it's going to be cheaper if you leave this on, but and they're kind of like, well, yeah, I don't care how much it costs me. I want to feel hot air coming out, So what can Eric, I mean, you've already got the guy up there, but how do we help people with that?
Don't blow air on people. I mean, literally. So to me, that goes back to proper air distribution, right? And when I talk about air distribution in that sense, it's not ductwork, right? This is air distribution in the room. Where are we blowing that air in the room? And we want to be blowing it on the surfaces that are taking heat out of the room.
Right.
Right. So if we warm those walls up, warm the ceiling up, typically it's not the floor. Most of the time it's the walls or the ceiling, losing heat out of a room. If we blow the air on those surfaces and we warm those surfaces up, yeah, nice.
100% genuine angry.
Ed, not the ungenuine angry Ed, right?
I think in Manual T they refer to it as there's an occupied zone and an unoccupied zone, and if you are not supposed to by any means blow any air into an occupied zone. It should be in a place where humans don't inhabit in the home, right?
Right. Yeah, I mean, and that occupied zone is what, like 2 or 3 feet off the wall generally?
I think it's 2 feet. It's like a 2-foot box around the room.
Yeah, around the edge, the perimeter of the room. So meaning
right.
your walls and your walls and your ceiling.
Right.
Not, you don't want to blow it on people's feet either.
So the comment that come up here, I think, is what my mind's been going to as well. Is, that's all fine and good, but when you're converting, when you're taking a gas furnace out and you're putting a heat pump in, you already got not only the ductwork in, you already got all of the registers in, and that means if you're going to do this, you're looking at going to that homeowner and saying, okay, by the way, while we're here, we need to give you the cost of replacing all of your registers. And making sure that we're blowing air in the right place. And sometimes that's possible. Sometimes the register location is just a terrible location. And unless you're going to relocate something, that's a hard sale. That's a really hard sale to deal with.
Yeah. Yeah. It can be a real big problem and or a real big challenge, getting that done properly. my big thing is work with proper register selection. Get something that keeps that air, in that range, that 2-foot range up against the walls and the ceiling, to make sure that you're not blowing it on people, because let's face it, we don't like cold air blowing on us most of the time, unless we're really hot. But the flip side of that is, if you keep those surfaces conditioned in the summertime, you're probably going to have less chance of being hot in there, because a lot of human comfort is radiant comfort. So if we heat all the surfaces around us, we can actually survive, be comfortable in cooler air.
Correct.
Yeah.
Yeah. And a comment there, sweat isn't good on the windows. It is good to be able, and part of your sweat on your windows is going to be if you have stagnant air there. If you got air flowing across that's going to help eliminate that sweat sitting on the window. Air movement is your friend to avoid that condensation.
Right, because you're transferring heat into that window at that point in time. You're wiping that window down. You're bringing heat into it, whereas otherwise you got a little microclimate right there next to it that's controlled by the temperature of that window if you don't have any air moving across that window.
So just a thought too, when you're retrofitting heat pumps, I was thinking, I know a lot of people like assume this homeowner is not going to buy registers. They're not going to upgrade all the registers. But like the big thing right now is it's not mandatory to sell a heat pump. Most of the customers that I run into, they're requesting heat pumps because of the rebates in that. So I think that's like a package you could build and say, this is recommended. This is an add-on. Would you like this? And if they say no, then it's kind of, hey, you picked the middle package or whatever. And would you like us, if they have comfort complaints in the future, we could revisit the register discussion, right?
Well, yeah, and I wouldn't call that like I wouldn't talk about a register package. This is an airflow package to get the air where it needs to be in the room to keep you comfortable.
That's a good point.
And communication with homeowners is always the best solution up front. Not only communication, but documenting that hey, you're requesting a heat pump. A heat pump heat is known to be less warm than the furnace that you had in there. It's not uncomfortable if it's installed the correct way. And to do that the correct way, you really need to be able to move the air across the walls, across the ceiling, rather than on you. And so to do that for your comfort and your efficiency of the operation of everything, efficiency is probably a bad word there, sorry, your comfort, we need to look and correct any airflow that could make you uncomfortable. Having that conversation up front is key.
Exactly.
Yeah. So yeah, just to kind of summarize everything, typically a heat pump's always going to be more efficient. I think it seems like the reason that people have homeowners switch over is because of that feeling of cold air blowing on people. So finding ways to set customer expectations and talk to people about why that's happening, set up controls correctly so that you're still maintaining efficiency while providing comfort.
Yeah, I mean, I think controls is probably one of the biggest reasons, but comfort is always a concern in there. But if we set the controls up right, then we can keep them comfortable and have good efficiency.
So one thing I wasn't quite clear on is, do the controls, they turn on the auxiliary heat and then they turn it back off before it reaches set point? So they allow the heat pump to just keep maintaining. So they just kind of help bump it back up and then shut off and it keeps running. Okay.
Yeah, cool. It's basically a down staging. So it keeps the first stage on, which would be the heat pump, and then it cycles on that second stage and cycles it back off.
Gotcha.
And it definitely is all customizable on all of these controls. So like, I think everyone needs to understand, like, this is not by any means plug and play. You don't just hang the thermostat on the wall and flip it on and it's done. You really need to learn the individual control that you're using.
And that probably comes down to, in some ways, the homeowner, right? If they're willing to have a 2 or 3 degree droop, or if they're not, they say, I want it, always to be this exact temperature in my house, then you need to set that up for them to make sure that's happening.
Well, and
calculate that balance point for capacity, for how much that heat pump can do, and when it's going to drop off. It's that capacity balance point. I know you have a thermal balance point, I think is the maybe the more proper term, but capacity makes more sense.
I like
to me.
capacity balance point. Yeah.
It gives that definition rather than the energy savings balance point, which we discussed earlier.
Yeah, and something else too. Like, here's a suggestion for contractors. This is something one of my former employers did for the technicians as we went out to install things. They would hand us these controls 100% set up. Right? They had the power supply in the office. The service manager or the install manager, whoever was setting up that job, got all the information from the salesman about what they had sold to the customer. He would plug that thermostat into he had a sub base sitting there in the office for all these different thermostats. He would just plug it in, program that thermostat, hand it to us pre-programmed. So all we had to do at the end of the install was walk up there, plug it on the wall, and turn it in, because he had it programmed for what type of equipment we were putting in, all this other stuff, which made sure that everything was set up properly in that thermostat. Because one of the last things an installer wants to do is stand there at the end of a job programming a thermostat with the customer hanging out, looking over their shoulder going, why aren't you done yet? Well, I got to sit here and punch 500 buttons to set this friggin' thermostat up. To me, that was an awesome idea that is super useful. Now, obviously, if you're doing a service change out, it's different. But if you're doing an install, you've got all that information, you've got the balance points calculated, everything's already pre-programmed. You plug it on the wall, you turn it on, you show the customer how to run it, and you're out of the door.
Right. And one thing I don't think we really mentioned is thermal balance point is something that you actually get by running a manual J load calculation and then following the manual S process. That's a point that is actually given to you based on the performance data of the equipment that you enter in manual S.
Mm-hmm.
Yeah.
Okay. Any other closing comments?
Well, yeah, I could open up a big can of worms right now from this slide, because personal preference and more than that is, if you're putting a dual fuel and a second stage gas furnace in with a heat pump, you want that coil before the furnace, not after, because if you do it according to this picture here and you're cycling that furnace on, as we've talked about cycling the electric resistance heat on, you're going to put so much heat on that coil that you're going to trip the limit. Or if it's an inverter, you're going to cause it to go crazy.
You can't put that coil before the heat exchanger, though, because you'll rust the heat exchanger out in the summertime. Seriously, you'll cause condensation in the heat exchanger, because you're blowing cold air over top of that heat exchanger.
Correct.
Yeah.
This is
that's where dual fuel, you can't run gas and the heat pump at the same time. So that's why you get that. You got to do one or the other. My only comment to that would be I've yet to see a stainless steel heat exchanger rusted out. But hey, I don't know. I've seen water running out of a lot of rooftop units with rusted out heat exchangers.
There you go. Yes. Back in the day, there were lots of them. I agree.
Well, there still are.
Gotcha. Okay. Yeah. Well, thanks for joining us, guys. It's been a lot of fun. I've definitely learned a lot, and thanks for tuning in.
See you next time.
Thank you.
Thanks, everybody.